Okay, so welcome also from me. My name is Eric Beckert. I'm actually the coordinator of the Horizon 2020 funded project iQonic, and I'm affiliated with the Fraunhofer Institute for Applied Optics and Precision Engineering in Jena in Germany. But this is at the moment less important, since I think everybody of you is interested what this iQonic project is about. And since we are quite at the end towards the project, we will in particular be able to talk about today about the results of the project. But as an introduction, what do we mean with the iQonic project? So in principle, it's all about photonics manufacturing. And when you are familiar with optics, photonics, optoelectronics, then you probably know that this can be a quite conservative and traditional technology or industry that is very often quite much hardware focused. So people focus, they have to focus on actual manufacturing technologies. You see a typical value chain on the top of the slide: manufacturing of optical components, prepare them, before the system integration, you have to handle those. Alignment is very often a very tricky thing in photonics, and bonding is required to provide a stable system. So all that is basically hardware technology that people develop to a very big extent in their companies and industries to provide superior performance of their products. So in principle, during these processes, there is indeed traditionally also a lot of data generated, but using this data, we believe, at least in the beginning of the iQonic project, we believe can be improved. We will later see that the usage of the data indeed provides quite much advantages. What is important for photonics? We very often have sophisticated products where we have this complex relationship between certain component and system parameters and the performance of the photonic product. And we also have to state that the performance of the photonic product is very often quite sensitive with respect to environmental conditions, but also to very dedicated component properties. And this was the general idea of the iQonic project. If we generate a lot of data during manufacturing of photonics, can we make a better use of this data to optimize the performance during the manufacturing? And you probably know that the zero-defect manufacturing approach is nowadays very well known in different types of industry. It is maybe not so common at the moment or at the beginning of the iQonic project also in photonics and the optics industry, and that was basically our idea. Look at zero-defect manufacturing approaches and try to apply them to photonics manufacturing. That basically means that we follow this generic zero-defect manufacturing approach that you see on the right side that was provided from the literature. And it is basically saying you have to detect something, you have to predict the performance, you have to prevent bad performances, and you have to take care that you maybe can repair components. or all these different items of a zero-defect manufacturing network we want to apply to the photonics manufacturing chain. And you can see that we did not only, or that we did not want to focus only on hardware technology, but we also want to include collecting data during the manufacturing, analyzing the data and making prediction and decisions out of the data that we generate during the photonics manufacturing value chain. Now, one might ask, why is that so important, for instance, for photonics? And I think there's a very strong argument that underlines why this makes sense to think about zero-defect manufacturing in photonics. And to underline that, I would simply point out again, photonics is really a cross-cutting technology that provides a quite big leveraging effect in many industries. You see that potential markets for optics and photonics and optoelectronics barely cover every item of daily consumer and also industrial life. And if we just take lasers, for example, we also have quite big revenues all over the world in this field. So this is a big market actually. But on the right side, you actually see this effect of leveraging the influence of photonics manufacturing. It's an example for lithography optics. The big player of lithography equipment is situated in the Netherlands, ASML. They create lithography systems, but they get lithography optics, for instance, from company Zeiss, and they get components for their lithography systems from other vendors like Qioptiq, Excelitas, things like that. And then they sell their machines for quite a lot of money, as you probably know, but these machines are then used to manufacture semiconductor components and electronic modules. So the result of the manufacturing of these machines is really the consumer market for electronic products. And this, I think, illustrates very well that the importance of photonics cannot be underestimated, and really working in particular here in the lower part, optics and systems for anything where optics and photonics can be used, does make sense to provide a good value there by means of applying also zero-defect manufacturing technologies. Actually, we did not investigate our project based on ASML lithography machines. I have to say, we are a little bit more, let's say, relaxed about the complexity of our systems. Nevertheless, we investigated very interesting use cases in the project. We have our partner Ibis Lasers, who manufactures quantum cascade lasers for various types of, for instance, sensing applications. We have the partner Prima Electro. They manufacture multi-emitter high power fiber coupled lasers for material processing. We have partners from Crystal manufacturing, the company Fila from Sardinia. So crystals for lasers that are then integrated into disc laser systems by our partners from the Czech Republic, Hylace. And we have a startup from Finland, Brighter Wave. They provide mass-produced, or they want to provide mass-produced miniaturized RGB lasers, prototyping them for various types of applications like augmented and virtual reality. So I think even though we did not cover lithography equipment, we nevertheless also cover quite an interesting scope for the use cases of our technology. And I have to say, in such a short webinar, we are definitely not be able to talk all about the exciting results that we revealed during the project. Nevertheless, we would like to show you a short, let's say, potpourri of what we did and what we developed in the project. So what will you hear about in the following? First, Sotiris from the Fourth Institute will talk about a scanning microscope that allows us to reveal something like subsurface damages in photonic chips, so generating information about defects in optoelectronics and photonics. We have the partners from Sensab and Holonics who will talk about how the sensor data, like from this microscope, but also from cameras and other types of sensors, is transferred by a middleware to a higher intelligence. Then we will hear from the partners from Core Innovation and from the Brunel University how this unified sensor data is actually analyzed and what you can see in this data. I think this is probably the most interesting talk, since we will see that a lot of things can be seen inside the data that the human mind and the human brain probably does not really see in this data. Of course, we have to do something with the data. Atlantis Engineering will report about a decision support module that helps the human worker in taking actions about what the data analysis revealed. And we also will see something about cyber physical systems, in this case for laser assembly. This allows for creating kind of a digital twin for complex optoelectronics assemblies that allow to compare what the data reveals with the model that is in the computer to allow for a better prediction of the performance and the manufacturing needs. We will end the webinar with a use case panel, not talking about all the use cases, but talking about the quantum cascade lasers from Alpes and about the high power fiber coupled lasers from Prima. And we will hear about how the application of iQonic technologies led to performance improvements in the manufacturing of these products. With that, I close the short introduction into the iQonic project and would like to hand over now to my colleague Sotiris from the Fourth Institute.
Thank you, Eric. Thank you, Elena. Thank you, everybody, for being in this presentation. I am Sotiris Mitrakopoulos from the Institute of Electronic Structure and Laser at the Foundation of Research and Technology Hellas here at Crete. And I'm gonna speak about our laser raster scanning microscope that we have developed here in order to be able to reveal defects that they are not seen by regular optical microscopy techniques. And those defects are actually below the surface of the samples. So this could be useful to identify and probably be able to see with high resolution possible defects in the samples that we want to examine. So this is a schematic of the experimental setup that we have developed. We are using a femtosecond laser. This laser is in the infrared, is 1030 nanometers, and it has a pulse duration of approximately 70 femtoseconds. And this laser, it is entering a microscope, and it is focused using a high numerical aperture objective into the samples. But before this laser enters the microscope, it is passing through a pair of galvanometric mirrors. Those mirrors are very, very small mirrors in order to avoid inertia problems, and they are moving very, very fast in order to create this raster scanning seam, as you can see here. So the laser beam is passing through the pair of the small galvanometric mirrors that they are moving very, very fast, and then the laser beam, it is focused onto the sample in order to create this raster scanning seam that we see here. Now, the detector is a photomultiplier tube. It's a very sensitive detector, and it is recording voltage values for every position of the beam into the sample. So very, very fast, for every position of the beam, the detector is recording a value, and then our program reconstructs these values into a contrasted image, and is creating actually an image. And the whole process, this whole process is taking approximately 1 second for every frame for 500 by 500 measurements, or pixels if you like. So for 500 by 500 pixels image, we need approximately 1 second. By using a high numerical aperture objective, we can accomplish a resolution approximately half micrometer radial resolution. So this is a video here that I'm showing you. It's real time. You see the laser beam. It is in the infrared. You cannot see by eye, but you can see here in this IR card. The beam is raster scanned. This is below, behind the microscope. You see the beam is passing the mirrors through the galvanometric mirrors, and is creating this raster scanning seam that you can see there. And then is this beam, this raster scan beam is focused, is reaching the objective lens of the microscope, and it is raster scanning the sample. So for every point of the sample, the detector here then is reaching the detector. This photomultiplier tube is taking a measurement, and we are gonna have the creation of an image. And of course here we have placed appropriate filters in order to eliminate the laser and allow only the useful signals that we want to record reaching the detector. Happens when we use this femtosecond laser. Here is fluorescein, a liquid, and you can see here is the surface of this medium, and the light, the spot, is this one here. So actually we are below the surface, and this spot is what is raster scanned below the surface of the sample. Of course, by moving the objective up and down, we can move this spot up or down and have very nice axial resolution. We can choose actually a layer, a surface layer, a layer inside the sample that we want to examine for defects. Because we are using IR, long illumination wavelengths, we can go much deep into the sample. We can reach approximately of in 1 millimeter depth in high scattering samples by using this femtosecond laser and this raster scanning technique. So this is a CCD image from the quantum cascade wafers from ALPS lasers used to create these quantum cascade lasers. This is a magnification of the CCD image. Here you can see high resolution imaging of this wafer that we want to examine for defects. You can see them here. And by using these images, these CCD images, we can identify in the surface of the wafer defects. And here is the CCD image from our microscope. And here is the image that you can see if we use the laser raster scanning technique that I just described you. We can clearly, by comparing the CCD image and the image formed by our microscope, you can see here fine details that they cannot see in the surface of the sample. Those features are below the surface and we can clearly reveal them. So in case there is some defect there or damage below the surface, we can identify it with our raster scanning microscope. Here is more images. This is the CCD image and this is the laser raster scanning image, and you can see here this feature which is needed for the quantum cascade laser to work, to have this wafer working properly, and we can clearly see that we revealed the features below the surface. Those images are collage images, so an image is much smaller, it could be like that, and then we can collage them in one big image and have large area images. Here you can see how you can have this with CCD camera in the surface, and here you can see how we can reveal below the surface these details. This is another wafer. You can see these green lines here with the CCD camera, and here you can see how it looks like with our microscope, and it's clearly seen that we can reveal defects that they are not visible using the simple optical microscopy techniques, but using these laser raster scanning techniques that we have developed at FORTH, the Foundation of Research and Technology Hellas. And here are more details, more examples of this kind of defects. You can see in the edges things that they probably they affect the performance of the quantum cascade lasers, defects that they are in this wafer. And that's all. I would like to thank you for your attention.
Okay. I am George Kouzas. I work for Sensor Suisse. My position is a research manager to the company, and I will present the data collection solution for the iQonic project. First of all, this presentation will be split in two sections. The first section will be the data collection per se, and the second one will be the data, let's say, availability, the middleware that will be presented by Stefano from Photonics. I go directly to the presentation. The solution for the data collection for SenseUp is the Dallos APK solution. This is a modular solution. This means that consists of a set of services or solutions that we provide to the field. Initially, we have some in-house sensors that are related with the quality inspection. These sensors are specialized for the graphic cards and the packaging industry. The second part of the solution is the data collection per se from other sensors or machineries. We can support a variety of protocols, and it is compliant with the most industrial sensors. The third part is the data processing. Since we have different protocols in the field, of different communication channels, we have a processing step to these data in order to provide a predefined or a homogenized format for this data. Another part is the real-time monitoring. This depends on the sensorial values that we acquire from the field. And finally, is this solution acts as a gateway in order to communicate with cloud-based platforms. For example, we can see here the communication with the Holonics middleware. This is some supported protocols and technologies that are inside the Daedalus ITK solution. As you can see, we can support the most of frequently used protocols on the field. And the installation and the deployment of this solution, data collection solution, is, as I told you, modular, so depends on the needs of each pilot. We can install a part of the modules or the whole modules that are provided by the solution. Usually, we use Siemens equipment in terms of gateway, PLCs, and etc. But the solution per se, if, for example, we need to install only the software part, can be deployed to any other kind of hardware. For example, in some cases that we need to pre-process, to process images, we can deploy to a typical server. Let's go now to the part of the iQonic. The Daedalus ITK solution is instantiated in two pilots, Prima and Filar pilot line. In Prima, the main scope of this solution is to collect data from the iQonic machine and push this data to the upper layer. Currently, we integrate it with the iQonic machine, and we get 10 different data channels. These data channels provide data that are related with the machine state and the processing stages of the optoelectronic devices. To the Filar use case, it is slightly different. Filar use case is more different as pilot from the Prima. We have many different demands. So the Daedalus ITK in this pilot is integrated with a variety of external sensors that monitor the production. For example, quality of the liquid, the weight and the distance that is forced to the sonotron in order to achieve the drilling process. Also, some vibration sensors are installed in order to monitor the vibrations to the machinery. Except this, we have the communication with the ultrasound machine and get parameters that are critical for the signal, the ultrasonic signal, frequencies, the status, and the output. Finally, the monitoring module is deployed to this solution in order to have a view of the production line. In both of these pilots, there is the integration with the Holonics middleware. In practice, we collect this data, transform this data to a specific format, JSON format, based on some specifications that are provided by the middleware, and will be explained to the middleware part of this presentation. Finally, we had just as a proof of concept in the iQonic system, we have connectivity with the integration with the SACMI electronic nose. The SACMI electronic nose provides a web service interface in order to make the sensorial data available, and with integrating with the segment, we can send this data to upper layers too. More or less, this was the presentation for the data collection. The next step is the middleware, where all this data goes from the data collection module. I would like to thank you, and if there are any questions, you can. So, Stefano, you can continue.
Yes, sir. Hello, everybody. Can you hear me?
Yes.
Okay, so I go to the presentation mode. Let me know if you are able to see the screen, the presentation. So, good morning, everybody. I'm Stefano Borgia, Engineering Project Manager from Holonics. I don't know if there are some external stakeholders respect to the project, but in any case, Holonics is a small medium enterprise that is providing some IoT solutions supporting the machinery management and industrial asset management. Here I'm going to present the iQonic KBS that basically is an industrial IoT software modules for the communication between different IT modules for the big data management and for the possible monitoring of industrial asset. It is a prototype that is an evolution of a part of a data management infrastructure that is present in Holonics. So the scope of this tool is to handle the storage of product, machine, and process data, the storage of the sensor data, and the information about the product quality for achieving the zero defect. That is one of the main tools of iQonic concerning the photonic industry. And based on the user definition, is it possible to define inside the tool some reference models and a snapshot, and also some custom data structure and schema in order to formalize and enable possible following reasoning on the stored information. Here I provide you a list of the services that are exposed by the KBS that basically lay foundation on Microsoft service-based architecture. And as introduced by Georgios before, KBS provides a data collection layer on the cloud toward the fields in order to gathering the sensor data that are coming from gateways and sensor. It provides edge-based processing facilities and provides long-term time-based data storage. And then there is another layer that is aiming at make the streaming of the data in real time to support the process data and application integration. And we have also some feature that ensure internal security, addressing and authorization. The main features that we are exploiting in the iQonic project is related to the possibility to enable data interoperability, defining some data structure, and the possible annotation of the data that are flowing inside the system. Here I'm presenting only just some indication about the main technologies that we are using inside the tool. So basically we are using the most known technologies in terms of NoSQL database and streaming data such as Kafka, and also about the technologies for the deployment, in particular Docker. Now we are addressing an evolution of this technological layer that is behind the tool. In particular, we are trying to move to Kubernetes in order to enable also a local deployment and not only a cloud deployment. In particular, in order to go and address some aspect of data security, confidentiality, or assessing problem of local networks and so on. And here you can see some snapshot of the application. In particular, here I'm proposing the snapshot of the part of the tool that enables the definition of the data structure. So given this tool, the user can explicitly define the semantics, let me say, of the data that are flowing into the system. And so basically we have some degrees of freedom in managing the data that are coming from the fields with the condition that this system is mainly supporting time series data. So this is the main difference with respect to other tools such as the high-level communication middleware from Atlantis, that instead is aiming at managing other data, for instance, coming from ERP and so on. Here I would like to share some information about the current application of the KBS. And in particular, in the iQonic project, we have two applications related to prima use case and filler use case. Basically, the aim of the use of the KBS is the same inside both the use cases, because basically the KBS represents the point of integration between the data loss gateway provided by SynSAP, that is responsible for collecting data from the sensor, and the iQonic platforms that with the terms iQonic platform, we are intending the system that is composed of all the other modules provided by the partners, aiming at performing diagnostic and prognostic. And so the KBS is also the knowledge base, so basically the big data storage that also enable the possible later data retrieval of historical data, and not only the data streaming. And so basically the KBS in these two use cases distributed the real-time data, sensor data, gathering in particular from frequent machine, and exposes the persistent long-term information to the other modules that have to perform diagnostics and prognostics action. And basically this is the summary of we are proposing, and this is an exploitable results of the project that we would like also to improve and to go on in this direction in order to take this product inside our tools and our software products after a phase of, let me say, commercialization, but also a phase of industrialization of this solution that is currently a prototype. And this is all from my side.
Thank you, Stefano. Thank you very much.
If there are some possible questions or comments.
Okay. We will have some times at the end for a Q&A, or you can write the question in the chat and I'll check. Okay, now I'll give the floor to Brunel University and Core Innovation for their presentation. We are a bit late, but if we stick to the time, we can make it. We cannot hear you, Nikolaos. You're muted.
Hello.
Okay, now we hear you.
I will share my screen. Can you see it?
Yes.
Okay, so first, Spiros.
Presentation mode.
Yes, please. Spiros, if you may.
Yes, thank you, Nicholas. Hello to everyone. This is Spiros from Core. We have prepared a short presentation regarding the sensor analysis. Next slide, please. Thank you. Specifically, within the iQonic project, Core has developed a new complete framework for defect detection and quality prediction of a final assembly product in two demo cases, Alps and Prima Electro. Next, please. Thank you. Regarding the Prima demo case, we have two components, the early anomaly detection with the developed deep learning algorithms which detect anomalies in assemblies from data logs and images from real to 50 module, and the accurate prediction with the developed deep learning models to predict the total power of an assembly for images and data logs of production stages for BL 250. In this slide, we can see the high-level description of an anomaly detection model. More specifically, our model takes as input data logs from 20 diodes from SAC production stage, mirror near field and mirror far field, and gave us output if the module will be defective with total power below 73 watt, or normal with total power above 73 watt. Next, Nicholas, please. Thank you. During the validation phase, our model, we achieved very promising results. From confusion matrix, you can see that the anomaly detection model predicts correctly all the normal assemblies and 55 from 58 defect assemblies with only three false positive. And this is a good start point. Next, Nicholas. Thank you. Now, regarding the accurate prediction using images, our model takes as input now images from 20 diodes from these stages and gave us output a number in range 73 watt and 93 watt. And during this validation, as we can see from the distribution error, from the distribution plot of error, most of prediction errors accumulate near zero. And as it can be observed, the majority of the error values are within plus or minus 2 watt. Okay, now regarding the Alps demo case, we have developed the accurate detection module with developed and updated deep learning models for image effect detection in different components of a final assembly product. And then our model takes as input a wafer image and gave us output a segmentation match. And as we can see, a core deep learning model predicts correctly the defective area with red color, and the by design area with green color, and the normal area with yellow color. In conclusion, regarding the Prima demo case, we have developed a new framework for quality prediction of multi-emitter product from early stages with very promising results. And in Alps demo case, we have developed a new solution for image effect detection, which is focused on defect identification of the wafer parts with very good performance. That's all from core site. I would like to thank you for your time, and I give the floor to Nikolaos to continue the presentation.
Thanks. So this is Nicholas Markatos from Brunel. I'm currently a PhD candidate, and I will present Brunel's progress in work package 6. We had two tasks. One was for defect detection, and the other one was prediction cost functions. So let's start. So the first one, we focused on both use cases, ALPS and Prima. In ALPS, we focused on images. So we had a wafer image, which contained hundreds of individual chips. In order to classify them, we use the convolution neural network, and the assessment can happen on real time or on chips. So from wafer image, we had 14 defect samples, 6 dirt samples, and 384 normal samples. As you can see, the dataset was imbalanced, and this produced problems for the neural networks to train. So for that reason, what we did is that we created synthetic images that are really close to the real ones. This was also verified by the experts, by the ALPS experts. So with this method, we upsampled the dirt and defect class to 394 as the normal class, and now the classes are balanced and the models can be trained. As you can see here, on the left, you have some real dirt images, and on the right, you have some fake dirt images. As you can see, they look alike. The fake images look like the real ones. And now we could proceed with the training of our algorithms. 80% was used for training and 20% for validation of the dataset. We implemented the CNN, convolutional neural network, with 4 convolution layers, 4 pooling layers, and at the end, 2 fully connected layers. As you can see, the classification was good. The training accuracy was around 80%, and the validation accuracy around 91%, showing that the algorithms perform well. As you can see here, it's a confusion matrix. So on the top, it's the predicted labels, and on the left are the actual labels. As you can see in the defect class, we scored 57 correct. They were defected, and we classified them as defect. 3 were misclassified as dirt, and 16 misclassified as normal. In the dirt class, all of the samples were correctly classified as dirt, and in the normal class, 74 were classified correctly as normal. 1 was misclassified as defect, and 1 was misclassified as dirt. On the right, you can see the evaluation metrics that we used to evaluate the performance of our models, which was the precision, the sensitivity, and the F1 score. So now, for the Prima case, in this case, we used tabular data. There were numerical data from the assembly process. We followed 4 steps. The first one was the expertise. So we collected expertise and knowledge from the experts on the field, and we gathered all the information. Then we applied some future selection algorithm that we proposed, the hybrid method. I will talk about that later, in order to identify the best inputs and the most important ones. Then we cross-validated these results with the experts in order to fine-tune further our models. And our aim was to predict the final output power of the module, which is called sum power. So pretty much during the whole assembly process, what we're trying to do is that we're trying to predict what the final power of the module will be. And in case that we see that it's going to be low or below the accepted threshold, we can stop the process or rectify something, etc. So Prima provided us with datasets for 2 of their products, the D-Series laser module and the S-Series laser module. Pretty much they follow the same assembly philosophy, but we decided to build our framework on the D-Series module due to the higher complexity in architecture, and then transfer it to the S-Series module. And the completed framework consists of 2 parts, the future selection in order to reduce the high dimensionality, and the prediction part. So for the future selection, What we did is that we did a research on the area. We tested many standalone methods, and also we proposed 2 hybrid ones. And in the end, we saw that the RLIF RFE that we proposed was the best method because it reduced the predictors from 1,181 to 123. And at the same time, the metrics, which were R square, root mean square error, and mean absolute error, remained high, and at some times they performed better than the original dataset and the other methods. And on the top right, you can see some of the important variables that our methodology extracted. Now, the second step is the prediction model. In this case, we divided the whole assembly process into many steps, and from these steps, we highlighted some crucial steps. We chose the crucial steps based on the amount of information in these steps, what they do. For example, if there is a change, let's say an assembly change, so for example from the FAC we go to the SAC, etc. So in the end we found 8 crucial steps throughout the assembly process, and in these steps we applied our prediction models, and we get something like the one that is showing at the bottom of the slide. So when a step is complete, you get a suggestion based on the predicted value of the output power. One important aspect is that for our deep multi-layer perceptron networks, we had to do a hyperparameter tuning. We had to tune the nodes in the hidden layers. We had to tune the dropouts. Actually, dropout and batch normalization are 2 regularization methods in order to avoid overfitting and boost the performance of our models. And as you can see, in model 6 and model 7, for example, where the complexity is high, we needed more layers in order to depict the truth and actually make accurate predictions. So these are the metrics for our models. On the right side, you can see the RMSE and mean absolute error. You can see that as we go through models 1 to 8, these errors are decreasing steadily. And on the left, which is the most important, you can see the error percentages. The error percentages are calculated based on the root mean square error. So for example, when you make a prediction of, let's say, 75, you know that you will have plus minus from 5 to 3.5%. And this depends on which stage of the process you're in. We chose MLPs, as you can see, although they do not have the best test error. The thing is that they have a similar train and test error, and this indicates that overfitting has been avoided. Whilst in the other methods that were tested, XGBoost and random forest regression, you can see that the train error has a high difference from the test error, and this signifies that there is overfitting. I will give you a demonstration of how it works. So we found a defect laser module with a power of 69.75 watts. On the bottom right, you can see the thresholds. So pretty much below 73, it's not acceptable. Between 73 and 80, the power is low. We can consider it as okay, but what we aim to produce is power over 80. So in the first steps of the assembly, steps 1 to 10, we predict 77.3, which is low. So far, no defect has occurred in the assembly, and we can proceed carefully with the assembly of that module. In the second stage, in the second crucial step, which is step 20, we again predict 77.3, meaning that everything is going as planned so far. We're going to have a low power module in the end, but still there is not a defect that puts it under the threshold. Here, at the third crucial step, we can see that the predicted output power is falling. It's now at 73.3. This is a bit alarming because as we progress, now our module is on the verge of the threshold. Here at the next step, we see 75.9. This might be due to a really good placement that pretty much rectified the previous errors, or there was a manual intervention in the assembly process that actually fixed something, or it's a statistical error that it's not significant at this point because our module is still on the verge of the threshold. And as you can see here, the predicted output power is below the threshold. So at this stage, the expert can say, okay, this module is going to be faulty. Let's take it out, reassemble it, or recycle the materials, or make minor adjustments in order to improve it. As you can see, and it goes forward, the predicted power is way below threshold, so pretty much this is an abort. You cannot continue with that because the module will be defective. And as you can see, okay, there is a rectification here now, probably because of the polarizer that boosted the power, and at the end we get the same predicted power as the actual pretty much. We predicted 69.8 where the actual was 69.75. So as you can see, from step 41 to 50 of the assembly process, you can say, okay, abort that module, save the material, save time, and save also energy. The next task that we focused on was the cost functions, the cost models. We chose the routine maintenance frequency as the control parameter of the cost model. So pretty much how frequent maintenance will take place on the machinery. The machine processing time was also selected as the controlling parameter, and in order to explain a bit the maintenance frequency, if we have low maintenance frequency, this means higher probability for defect. If we have high routine maintenance frequency, this implies that we have to pay more for manufacturing costs. So what we have to do is that we have to find a trade-off and balance between product quality and cost, and also time. What we did is that we got some data from Prima, and also based on previous research that we've made in similar projects about optoelectronics, we managed to create two equations that actually depict the resource utilization versus the machine cost. So pretty much how intense you use the machine and how frequently compared to the machine cost. And that produced us the final product cost versus routine maintenance frequency, which actually shows that in order to achieve good product cost based on the routine maintenance frequency, you have to do around 12 to 13 maintenance per week. Thank you for your time.
Thank you, Nicholas. Okay, now we give the floor to Atlantis for its presentation.
Hello, everyone. Let me share my presentation. Okay, can you see?
Yes, we can.
Okay, thank you very much. I'm Zisis Keroudis. I'm from Atlantis Engineering, and today I will present you the defect detection decision support system. Sorry. Okay. Well, the content of this presentation is based in 5 sections, starting from the aim, a brief overview of the solution pipeline, the specifics of the Alpes use case, and finally, the user interface and features of the DSS, and the results and the next steps. Well, before developing the tool, we wanted to set clear and oriented goals towards addressing the needs and the requirements. In this case, the development aim is focused on 4 different pillars. First, to design and develop a defect strategy for the defect types and the user qualification techniques, while also categorizing the product and decision-making processes. Another pillar is the risk assessment management in the decision-making processes in order to support the user in taking the best possible action. The last one is the aspiration and achievement to create an independent system to assist the end user in optimizing his processes in the production by offering him solutions on the shop floor. However, each use case can have different needs and requirements, and so we had to be a little more specific from the previous aim. In this case, the developed tool is oriented towards the ALPES use case. ALPES is a semiconductor laser power production company. So the aim for this tool was more specified towards providing the end user a friendly and interactive interface, supporting him in identifying the defected devices by offering him result visualization reporting. However, although the tool developed based on the ALPES use case with the right parameterization can be considered a valuable tool for all the optoelectronic field. Now, just to say a few words about the solution pipeline. The developed solution consists from 4 steps. The image collection, in which the device images are collected from the field, in this case the ALPES use case. The device mapping, which supports the actions to bring the images in the desired visual state, and the defect detection, which is used for the detection of the defects. The DSS is the final step of this 4-step approach, and it is used for the evaluation of the output of the previous result. Now, the DSS collects all the previous information, all the previous information, enhances it, and with additional defect categorization, and can support the optoelectronic engineer by an interactive and friendly user interface to take decisions. Now, during the whole process, the data are transferred with the help of the higher level communication middleware, automating also the whole pipeline. Now, as we have already mentioned, we have focused on the ALPES use case. Now, this use case involves the detection of the failures before the wafer slicing, while the provided result visualization reporting can support the user in taking decisions regarding the devices on the processed wafer. The basic characteristics of the use case includes the aggregation of the failure detection results from the technology providers and assisting the end user with an interface to check the failures on the wafer. Furthermore, the DSS can provide a report with a ranking of the defected devices, supporting further the user in discovering correlations and performing further analysis. Now, the whole process starts with the wafer. This is why the system periodically checks for any new wafers. In this slide, we can see one of the interfaces of the DSS. The DSS can list all the collected results which are produced by the device mapping component and the defect detection component. And the user has the ability to view only, however, the user has the ability to view only the wafer for which all the results are collected in order to have a complete overview of the produced devices. Now, moving to the second interface of the DSS, after all the results are collected, the DSS can visualize and report to the user all the information. In the figure, we can see a wafer with the devices. The colored devices here are the ones for which defects were found. The interactive part of the system offers the ability to check the position of its device on the wafer and identify the defected ones. So all the obtained results can be searched by wafer and by device. Now, for each device, the DSS estimates a degree of defect, while facilitates further the processing by ranking the devices based on the defects they have. This can be achieved by setting a defect-no defect ratio to each device, assisting the engineers in identifying and selecting desired devices. An additional feature lies on the customization by the end user, adjusting the characterization thresholds based on his needs. Concluding on all the above, a tool was developed to support the optoelectronic field by offering an interactive and friendly interface and supporting the engineer in detecting the defects as well as estimating their degree on the devices by visualizing the results and creating reports for the user convenience. After discussions with Alpes, a few additional features are proposed, which can also be potentially new additions to the tool. For example, the plotting of lines on the wafer to show the cliffs, or some more plotting properties. Sorry. Thank you very much for your attention and your time.
Thank you very much. Okay, now last presentation from Politecnico di Milano.
Yes, hello.
Hi.
Okay. Let me put it in the presentation mode. Okay, thank you. My name is Ozan. I'm from Politecnico di Milano. I'm a PhD student. And as the work package leaders of Polyme, we had several objectives. The first one was to employ a defect management strategy for different defect types, to provide a decision support system for analyzing the severity of defects and to provide rework, reuse, or recycling practices, to deploy techniques for reuse or requalification, to develop a cyber-physical system for online defect management and requalification, and lastly, to develop a decision support system to manage reverse supply chain. So here, as task 5.4, we had to develop the cyber-physical system. So this is the PER chart connecting different tasks within work package 5, and here we are at task 5.4. So the objective was to design, implement, and test a cyber-physical system in the lab scale, basically, for controlling at the shop floor level the activation of reuse and requalification operations defined in task 5.3. So the first action that we had to take was to design the specific CPS architecture, then development of the model that represents the intelligent modules to be integrated, then the integration of the whole cyber-physical system into a unique intelligent control unit, which usually visualizes the outputs to the shop floor operator. So as the output, there should be the first the software module integrating our capabilities. Then secondly, the document describing how to integrate these functions into production system and interoperability requirements. So this is the first architecture that we have designed. So basically, to start with inline inspection and measurements of single components, we measured the key quality characteristics of a single component. Then this information is shared with classification module to activate the sorter, which serves as the clustering of components into different quality classes according to these parameters measured. And the buffer levels and the mean class related statistics are shared with assembling module, which provides the optimal selection and alignment of components into the laser module. Then this information is provided to selector, which is controlled by an operator. And then final assembly station receives this information and performs the assembly. In the meanwhile, there is human in the loop algorithm that is keeping the user into the cyber-physical system that is also contributing to his learning activities and their personal development. So step one was the definition of key quality characteristics and then inline measurements. So we have the single component performance. So this component performance is combined with selective assembly strategy, which I will define in the next slide, and goes into optimal selection of components and decision of module configuration. At the end, we have this optimized selection, which is combined with online measurements to decide the optimal alignment. So we have the optimized assembly. So the classification module, as I mentioned, sorts the batch of diodes into different quality classes according to their characteristics. So they follow these bunch of different mathematical formulas, but we have already discussed these parts quite often. So I'm going to briefly describe. So there are different class limits decided by the shop floor operator. And if the parts quality characteristics are matching with these limits, they are classified into corresponding classes. Otherwise, they are discarded. So at the end, these buffer levels are dynamically adjusted and updated, and they are the mean quality characteristics of the parts stored inside of these classes are updated accordingly. And then this information is shared with assembling module, as I showed in the architecture, to find the optimal selection. So what this optimization algorithm does is to solve a fourth order nonlinear problem with nonlinear constraints and integer variables, because we are dealing with single diodes in laser industry, and they cannot be continuous variables. So at the end, what we were trying to do, especially for Prima use case, is to minimize the gap between the predicted output power that is coming from product meta model and the target output decided by the user based on their application. So the selection matrix, which is defined as alpha, has to be between 0 and the maximum number of available units in the buffer, and the power output should exceed the target power. So how we decide the output power is basically the summation of power of single components that are selected to be assembled. And the average wavelength of this unit is again the average wavelength of the selected diodes. But especially the positioning of these diodes are very, very important, because the average wavelength is affected by the temperature under working conditions. And as you can see in the figure, this efficiency of the fiber laser module, which is called the assembled part, is affected by the average wavelength. So there is this output power is affected by the efficiency. Efficiency is affected by the wavelength, and the wavelength affected by the temperature. So as you can see, this modeling part is quite complex to be solved. And there are different zones that are based on the number of components that you want to store. So at the end, the extended wavelength based on their positioning and the locations are systematically calculated according to these formulas. So as the optimization algorithm, what we used as genetic algorithms is basically very much related to human environment. It creates an initial population and scores this population, basically evaluates the best combinations in this population. So retains some of parts as they are for the next generation. And some selected parents produce crossover and mutations for the next population. So we select some random specimen and find the best specimens inside of this group, breed some new generation based on crossovers and mutations. And some mutations are, of course, randomly, and they are completely diverse. And then we go on with this iterative process. So over successive generations, the population evolves towards an optimal solution, which are elites remains as elites. Mutations are completely different from the previous population, and crossovers are the mixture of the parents. So what we have defined and produced is the control unit for the shop floor operator. And when we click on settings, it appears some different metrics as I explained in the selective assembly part. So the operator can clearly work on these different parameters. And when we go into classification module, this is the main screen appearing. So on the left side, you can see the data plots that you are using. Then there is batch statistics. Basically, depending on the different batches you select to classify, you have the statistics. And when you click on classify diodes button, you obtain the classes and the wavelength and which multi-emitters are going into which corresponding quality classes. So going into assembling module, on the left side, you can see the buffer level distribution and the corresponding class related statistics. So when you click on the optimal selection button in here, it initializes the genetic algorithm, it evaluates the optimal solution, and provides you this screen. So on the left side, bottom left, you can see the output target power that is entered by the user, the average wavelength decided by the end of this whole procedure, and the efficiency, what is the power input and what is the power output, what is the objective function, which is defined as the gap between these output power and target power, and the number of units used inside of classes. So on the right side, you see the optimal selection matrix, basically telling the operator from which class he should pick up the diodes and put it into which zone exactly, and what is the expected values. And here is the optimization summary. How long does it require to optimize, how many generations and evaluations, etc. So these parameters are fixed by us, but depending on the request, we are able to provide how to play with them as well. So as an experiment, we selected 312 diodes between these corresponding dates, and we performed 3 experiments. So in the first one, we assembled total number of 20 modules, 10 with first in first out strategy and 10 with selective assembly strategy to compare the results. In the second one, the total number of 4 modules are assembled with selective assembly and only 1 with first in first out. And on the third experiment, the 3 FLMs are assembled with selective assembly and 1 with first in first out. Just to give you some more insights, 1 first in first out, the results do not change since we use the same data, sample data coming from Prima. So we use just 1 assembly for first in first out to compare with different scenarios defined with selective assembly. So this is the first experiment. As you can see, in 10 different assemblies with first in first out, a selective assembly outperforms all these values provided with first in first out strategy. So it clearly indicates that our proposed approach is working and functioning well. And here, again, you can see when the number of classes are increasing, the optimization module and algorithm is able to find better solutions passing by time. Just because we are narrowing down the class intervals, it is more and more going into individual assembly side. But since the number of increasing the number of classes significantly requires more computational power and optimization time, until the certain point, we have to cut the experiments. And before having a complete production system model, it is very hard to decide which number of classes are the optimal, because it is quite heavily affecting the production system logistics as well. So there is the trade-off between the product quality, optimization, and the system logistics performance. So the trade-off has to be found. In the third experiment, the second experiment was with 13 number of units to be assembled into the module. If we go into 12 units, you can clearly see difference much better. When increasing the number of classes, the gap between output and target power is really getting close to the 0. But this is very tricky, because in the models, you do not completely model the whole behavior of the system. So you select some parts to be included, and you neglect some different characteristics and transfer functions between the parameters. So going into 0 may not satisfy the output target power in reality. So you should not exceed this limit too much. You should not elaborate too much on this line, but you might want to keep a bit more in the threshold. So the user manual, which is the documentation explaining how to use the software, how to install it, and what characteristics are there, is already provided to Prima as well for the first version. and it includes introduction, the process overview, the software, how to install, how to use, everything included. So this was it from my side. I would like to thank you everybody, and I'm here to answer if there are any questions.
Thank you, Ozan. Thank you very much. Okay, now we dive into the panel. In order to make this the use case presentation more interactive, we prepare some questions for them. I suggest we start with Alpes, with some question with Alpes, and Eric.
Okay, I hope that Jeremy from Alpes is in the line.
Yes. Hello, everybody. Can you hear me?
Yes, we can.
Yes.
Good.
Okay, Jeremy, would you first like to tell a little bit about your use case, and then I have some questions for you?
I think I have the slides to answer to your question, Eric.
Okay. So, Jeremy, we have seen that in iQonic we collect data, we transfer data, we analyze data, and we try to put data into models to predict the manufacturing of optoelectronic components. My question is, we applied not all, but many of the technologies also to the production of quantum cascade lasers. Can you say a little bit what are the key performance indicators that you find interesting that are relevant for the production of your lasers?
So thank you for the question, Eric. So just to give you a quick context, I will just present our company. So we are a small Swiss company of about 25 employees. It's a bit fluctuating these days, but at the time we're almost 25. And this company was founded in Neuchâtel in 1998, so almost 25 years ago also. And we were the first company to sell quantum cascade laser to university and to different customers. And for selling our laser, we have various packaging options, which correspond to different type of laser depending on the customer's needs. If they want to integrate them directly into their system, or if you want to use our laser directly with our kit. And also we develop a lot of dedicated electronics. For example, we develop some temperature controllers and also some electric sources to drive our lasers. So our chain for the quantum cascade laser fabrication is the following. So first we do some epitaxy. So this is the growth of our quantum wheels. So basically this is some semiconductors layers, small layers of semiconductors to make the gain region for our lasers. And the second step is to do the processing. So we transform these flat wafers into devices. So we make some ridges to make the optical waveguides, and we do all what we need to make the electrical contact and so on and so forth. And the third step is to slice the devices from the wafer and to make the die bonding and the wire bonding, so to put them onto support and to add some wires to inject the current inside the device. And the last step is to do the testing of these devices. So we, for example, measure the power and the frequency emission of the devices to see which device can be sold to each customers. And the two first steps are outsourced, meaning that they are done overseas, and we don't have a strong control on these steps. And the two last steps are done here at Alps. And they are very costly. We need to test a lot of devices to find the good one for our customers. So here the idea, the problematic was to find as early as possible the defective devices in order to not mount them and to test them, so to save some times. So for example, for controlling the frequency emission of our grating, we add some grating on the top of the devices in order to control the lasing mode emission, so to have some single mode emission frequency. And for each wafer, we have hundreds of devices, we have hundreds of chips, and each device has its own grating. And as you can see on the right-hand side image, we have sometimes some defects. So if you look inside the red square, you can see that we have some area which are gray, meaning that there is no grating edge during the process. So for some reasons, for this area, we don't have any grating on the top of the devices, and they can be considered as defective devices. So to find this area quite quickly and easily, a machine learning approach has been developed in the frame of iQonic by Kerr. And we can see that the correlation between the grating image and the prediction are really good. And using that, we can prevent mounting defective devices with no good grating. And to use this information, we just connect to the decision support system developed by Atlantis, which has been already presented during this webinar. And here you can see, for example, on the right, there is some numbers. So this is the name of the chip. And looking at this list, we can see which devices are the good one and which one we have to mount to have good laser at the end.
Okay, Jeremy, sounds great. And I also see that you have some ideas what could be future implementations of some of the iQonic technologies, right?
Yeah, so far I just presented some grating image analysis, but we also have some other image analysis. We also discussed with FOF about linear microscopy. They already present some results, but we also have some other idea in mind. And at the end, we also have a third application, which is a smart tagging for die tray management. So so far, I just presented the grating analysis, but we also, as presented by Brunel, we also have some wafer analysis. So this is the final wafer. And for this wafer, we do high resolution images using a microscope. And Brunel also developed some algorithm to detect the defective devices. And it was tested, and now we have to also integrate this part into the decision support system to have a global view of all the defects on the same application. The second possible improvement that we can have in the future is a nonlinear microscopy of quantum wells inspection, because the first step that we do for fabrication is this epitaxy. So we grow some semiconductor layers. They are very thin, about 10 nanometers. And very often we have some defects. We have a distribution of defects inside the structures, for example, dislocation or other kind of defect. And this is very challenging because we try a lot of different techniques for that. This is really important for us, because if this growth is not good, we should stop the process at this step, and because the next steps are very expensive. But so far, we did not manage to find a good method to really find the defect distribution inside our wafer. So we have some preliminary discussion with FOSS about this issue, and I think we should push that forward. And also one another topic in the ALP use case, which is almost ready for production, is the tracking of our die tray using some RFID antennas. So the die trays are used in our production to move the laser between the different steps of the production. So for the testing, the wire bonding, and so on and so forth, and also to stock the devices. And the idea here was to add a RFID tag on the die tray to store some relevant information and to improve the connection between the die tray and our database to really follow the laser between the different production steps. And also, we use this die tray to send some laser to our suppliers, for example, for optical coating. So we regret to improve this step using these RFID antennas. So I think that's all from me. So if you want to learn more about the use case done here at ALP, there is a paper published in the Frontier journal, and this is the four partners involved in our use case.
Okay, Jeremy, thank you very much. Sounds great. I think I can hand over to Elena and the Prima use case.
Yes, I saw Julia among the audience. Hi, yes. Julia.
Hi, good morning. Should I share my screen for some slides? to better focus on.
Okay, so for you, Julia, the question. So from the previous presentation, we saw what the iQonic platform offers, what iQonic project offers, which means a platform of zero-defect manufacturing by using strategies for increase the quality recycle and reconfigurability. So how these strategies that we had explained before can be implemented in the production of high-power laser in your use case, and how this strategy can improve the production in Prima Electro.
Yes. So basically, Convergent or Prima Electro. Convergent is the laser unit of Prima Electro. So we produce high power laser and diode laser and fiber laser for basically industrial market and material processing, but also medical market, particularly surgery and aesthetical. So within this project, we offer the complete production chain. So starting from the wafer processing and the single diode manufacturing, and then we have also the backend, so the packaging of more single diode inside a multi-emitter for basically two products of 970 nanometer, 920 nanometer, and we are also focused on the assembly of laser modules in fiber laser modules. So more multimeter diode that pump an active fiber, active doped fiber. In the project at the beginning, we focused on 4 topics. The first one is in the visual inspection of the single diode, and we asked for artificial intelligence algorithm able to classify the diode during the visual inspection that we perform on 100% of the devices. And so the classification in basically pass or fail diode. And then we also suggest an artificial intelligence able to evaluate the goodness of the assembly of the optics inside the multimeter modules. And another very interesting task has been a reverse supply chain able to optimize the time and synchronize the systems that are involved in the optical packaging department and also in the testing department. And a last task involves the optimal selection of multimeters that will be used to pump the fiber laser. So how this strategy improved our production chain, basically in time and cost, and also reclassifying processes. In particular, the first task that focus in the visual inspection with an artificial intelligence, we performed this process with an automatic system of pick and place. So the device is picked from this automatic system, brought in under the microscope, and then the operator evaluate if this device is pass or fail, and which kind of fail categories can be detected for that anomalies. And in case of the strategies implemented automatically, this could save a couple of minutes, and this means that in a production of dozens of devices for weeks can store a lot of time, of course. And then the second artificial intelligence support system, let's say, has been implemented in the during the optics alignments. We use for the optics alignment automatic systems. The process is quite longer because for every product the process of alignment takes 4 hours and a half. But after this process there is also a thermal treatment and then testing of the module that takes let's say 40 hours. And at the end of the testing process, frequently, well, not frequently, but for a certain percentage, we have some anomalies, and so we need to analyze the product, and sometimes we need to perform again the optics assembly. So we suggest an artificial algorithm that can predict the final power of the module during the alignment of the optics, in order to save the testing time that it's considered that more time consuming and expensive part of the process of the optics assembly. So in this case, the entire process could, that now it's taking 40 hours, could be reduced for the failed parts only to 20 hours. And another important point is that some anomalies in the optic alignments can be detected directly from the system, but some others not. We need an intelligence to detect some misalignment or some contamination on the optics. So basically, at the moment, only the operator could detect these anomalies during the process, but at the end we have many systems. So in case, so currently we can detect only, let's say, 1% of the anomalies within the entire production. But if we have an artificial intelligence that can monitor every process, I think that we can detect every anomalies and be able to repair the anomalies before the following steps. So in this sense, really well, the goodness and the quality of this kind of process. The third strategy, the reverse supply chain, is an analysis on the possible strategies that could be implemented if and in case a product doesn't pass the quality criteria at the end of the entire assembly. So we analyzed possible root causes, a list of procedures, and strategies of rework, or in case reclassify, or in case reject the complete part because not reworkable. So the first analysis that in this project took 1 year, the first year, has been focused in implement in the production line a failure analysis for the parts that fail the first testing and fail the quality criteria, for example, in power or reliability of some internal part of the multimeter. And the second, and this failure analysis basically involve one operator of the production and the same system of the used in the production. So in the second part of the project, we asked for a reverse supply chain able to organize the standard process flow, but also the second chain that some modules need in the assembly process. And this is very important to in order to have in order to save time and organize people that work on that. And of course, the strategy of rework and reclassify are used instead, scrapping the entire modules that it's quite expensive. And the last strategy is a cyber physical system able to consider the characteristics of the lasers, multimeter lasers, and also the characteristic of the fiber lasers, and choose an optimal set of multimeters able to pump the fiber, and at the end have a fiber laser with quality characteristic in terms of power and efficiency in target. And in this kind of selections are done now manually, and considering some internal strategies, but this process take more or less 50 minutes, and by using a tool dedicated, we basically save time because it takes only 5 minutes. And this is done for every fiber laser module, so for the entire production. So at the end, it's very useful because it will be used for every fiber laser assembly. So basically, we already implemented most of these strategies, and we are analyzing the effects, and we are and the results are very, very interesting in terms of time and cost effectiveness. So thank you.
Thank you, Giulia. Thank you very much. Okay, now I'll give the word to Eric for final remarks.
Okay, thank you, Elena. Since we are quite late in time, only one slide, final remarks. What are the key takeaways from this webinar? I hope we have been able to show you that if we gather and analyze data as early as possible from the photonics manufacturing chain, we can reveal really accurate prediction of the performance of the product later. I thought that was a quite astonishing result, that when you look onto chips, you can already know kind of how a later complete assembled systems based on these chips is performing. This is, I think, one of the key takeaways of the project. Additional takeaways are that you can, when you characterize very early components, you can reroute them to different types of products, and that you can prepare them even for an eventual repair or rework of those components. So from my point of view, these are quite significant. This is a quite significant progress towards zero-defect manufacturing in photonics, and I think we have seen that in particular for lasers, the technologies are very useful. If you like, you can get further information on our website or on the iQonic LinkedIn profile. And I understood that Elena also provided a feedback form. So everybody, if you like, you can raise your voice and point out your opinion about the webinar and about the content of the project in this feedback form. So that's it from my side. I hand over to Elena again.
Thank you very much, Eric. Yes, I share with you in the chat a link for a feedback form that we kindly ask to fill in. And again, thank you very much, everyone, for participating. Thank you to our speakers for their brilliant presentation. Sorry again for the inconvenience with the Zoom link, but thank you very much for staying with us anyway. And that's it. Thank you very much. We will upload the video on our website and social media. So if you know about someone who could not participate at the webinar today, you will be able to share the video with them. Thank you very much again, and have you all a very good day. Bye-bye.